welcome dear students. We are in the CEC Gurukul lecture and we are in the series of quantum technology. In this series we are discussing the quantum sensing, and quantum sensing we discussed the various quantum sensors, like we discussed the Rydberg atom, we just discussed the trapped ion, we discussed the neutral atom, we discussed the solid state spin, we discussed the solid state spin with the single spins. Moreover, we discussed the superconducting circuits, and at the last we have discussed the elementary particles based sensors. Now we discuss the other type of sensors, like what we are having, the SET, that is the basic the quantum sensor. Another is the optomechanics, another is the interferometer. So first we take the SET, that is employed as the scanning probe sensors, just to image the electric fields on the nanoscale and shielding light on the variety of solid state phenomena such as the fractional quantum Hall effect or the electron hole puddles in the graphene. So we prepare a sensor by using the graphene, and that is work for the scanning probe sensors that can image the electric field on the nanoscale ground, that will shielding the light on the variety of the solid state phenomena where we are having the fractional quantum Hall effect as well as the electron hole puddles, and that will give the basic structure of the element. So in complementary approaches, charge sensing by stationary SET has enabled readout of optically inaccessible spin qubits such as phosphorus donors in the silicon, that is based on the coupling of electrons. So we use this SET just for imaging the electric field. Now this advanced instrument combines the atomic force microscope, that is a AFM, elements with the single NV center, where we integrated the AFM into an optical system and placing a diamond with a single defect on the tip of the AFM, that make it possible to scan the NV sensor over the sample and create an image of the magnetic field produced by the sample. Now this invasive way of measuring that allows for the high resolution measurement of magnetic field, currents as well as the temperature, which is important for the metrology of the 2D material as well as the characterization of the semiconductor devices. So this instrument used for the semiconductor devices characterization as well as the metrology of the 2D materials. We can find the structure of the 2D material. So this is the tip from where which move on the surface, and that will scan all the volume or the surface of the material, and that is the parameter, that is the target preferences, where we are having the resolution, we have the sensitivity, where we are having the speed for the scanning of the surface. So this is the SET working. Another is the optomechanics. So phonons, that is the discrete quantized energy levels of the vibration, and have recently become accessible at the single particle, that is the level in the field of optomechanics. So which studies high quality mechanical oscillations that are strongly coupled to the light. So in this preparation of the phonon, number states and their coherent superposition remains difficult. So the device built to achieve these goals have shown great promise for the sensing application. So first the preparation of the photon number states and their coherent superposition, that is requirement for the sensing application. So this is mainly due to the fact that mechanical degree of freedom strongly coupled to nearly all external fields, and that strong optical coupling enables efficient actuation and readout of mechanical motion. So optomechanical sensors have been employed to detect the minute force, acceleration, magnetic field, spins and voltage. That has been published in various research papers. So by using the optomechanical sensors, one can find out or one can detect the minute or a very low forces, acceleration, magnetic field, spins and voltage. So while these demonstrations have remained at the level of the classical sensing in the sense of this review, so their future extension to the quantum enhancement measurement appears most promising. So there are the various methods by just making it update in the quantum sensing applications. So another type of sensing is a compact vectorial magnetometer. So in contrast to the previous instrument, this magnetometer uses an ensemble of the NV centers in the macroscopic piece of the diamond. So using many defects allows for a compact setup that can measure the highly sensitive vectorial magnetic field. So now if we are comparing these measurement of the local magnetic field to a magnetic field map of that of the area, these compact magnetometers can be used for position tracking and the navigation without needing GPS system. So directly we can navigate and we can directly track the positions. So another advantage of the compact nature of this instrument is that they can be integrated into other systems also that make them attractive technology for the automotive as well as the medical industry. So these are the basic points where we are having the target performance as well as we are having the resolution and we have the sensitivity for this instrument. So we can find out the various parameters by using this instrument. Another is the wide field magnetometer. So this setup uses an ensemble of NVs to measure static magnetic fields at the different location of the sample of the interest. Instead of using a photon counter, this instrument uses a camera to measure the magnetic field across a certain region of the sample in a single image. Means in a single image it can captures the various locations or various region or a certain region. So this makes the measurement process very efficient with a resolution that is determined by that of the imaging system and the camera. So you can see easily here is the target performance where we can have the resolution as well as the sensitivity, all having the different sensitivity or having the different resolution and they are having the different application in the various field. So another quantum sensor networking for the fossil energy application. Fossil energy means we are having the various energy efficient quantum sensors. So with the advent of the QIS, quantum networking opportunities for the safe and secure energy production, processing and delivery will surpass the opportunities offered by existing networking system. So these opportunities include the accessing actual data on the global CO2 emission. So we can, by using this sensing, we can find out the actual data that is from the, or we can find out the CO emission and other type of environmental degradation we can find out by this sensing. So fossil energy infrastructure automation where we are having a oil, gas and electricity infrastructure built and out and the planning. Another is the operational optimization of the interdependent infrastructure. So modernization of the grid with the quantum grid, that building transportation infrastructure and operation to support the advanced energy supply. So by this mesh type of structure we can capture the very efficiently, we can just measure, we are having a great sensitivity and we can measure the various defects or various pollutants. So quantum key distribution of the security and the reliability of the energy delivery. Now we discuss some of the existing commercial quantum sensors and its application. So what type of quantum sensors are available right now? It is a gradiometer. So if we first discuss the gradiometers. So gradiometers are among the most mature quantum technology currently available for the energy based application. So semi-classical quantum microgravity sensors are being developed at the lab scale and are being commercialized by companies that deliver the unprecedented levels of measurement, like reliability, accuracy for underground survey applications. So opportunities can also be realized by using the atom interferometry in the gravity survey application. So by using this type of sensor, which is very highly sensitive quantum gravimeter capable of detecting gravitational field through the material's density contrast. So by using this we can measure the various gravitational field. So it is portable for outdoor uses as well as, and has an increased sensitivity level that enabling the high resolution of either smaller or deeper features and compared to the existing instrument such as a CG5 as well as the CG6 gravimeter. So in geophysical surveying for minerals and petroleum exploration, most of the currently available sensors severely suffer from the unwanted spatially and temporally varying noises that will distract the signal and that is not from the interest of the target. So by using this quantum sensors, it is easy to detect with the noise free calculation. So from the data analyzed by the various researchers from the commercially available instruments based on the cold atom quantum technology in the gradiometer configuration and compared that with the measurement obtained using the classical gravimeters and how efficiently it is working. So they found that quantum gravimeters were 1.5 to 2 times more effective than the classical gravimeters in the ability to detect the small buried features, and that quantum gravimeters could measure at the greater depth. So by using quantum gravimeters, the energy can be find out at a very greater depth. So you can see through this diagram that the noise cancelling effect of the gradiometer configuration in comparison to the conventional gravimeter when measuring the same buried signal. You can see left hand side there is a gravimeter, that is a single sensor, but here gradiometer there are having the two sensors and easily it can detect the values and at the various field levels. So we can have the more efficient gradiometer. So this is a schematic diagram of the working of the gradiometer. Another is the quantum light detection and ranging, that is also known as a LIDAR. So quantum LIDAR is another techniques undergoing commercial development for the fossil energy application. So including the oil discovery, gas leak detection and the carbon emission studies. So during the LIDAR operation, pulse light is sent towards a target. As we are using the light, so pulse light that is having some interval, it is not a continuous light, sent to the target. So some portion of the impingement of the light is scattered back to the LIDAR detector that will detect the leakage. So by recording the time between the laser pulse and the detection across an array of the detector pixels, but that is the time lag between these two, it is possible to determine the distance the scattered light that is travelled and that enabling the 3D mapping of the terrain. So in quantum LIDAR, information is obtained by detection of the single photon. So, it is opposed to the conventional LIDAR. So, in the quantum LIDAR, information is obtained by the detection of a single photon. We are using a single photon, that's why, and it requires the detection of, but in the conventional we require the multiple photon, but through this we use a single photon, which allows for efficient rapid 3D mapping with the high resolution relative to the conventional techniques. So, companies that are in making this LIDAR are Quantum Light Metrology and ID Quantiq, among the others, have developed the commercially available high resolution single photon LIDAR that sources for the terrestrial mapping applications and the detection of the small gas molecules even in the harsh environment such as the survey. Now, you can see here we are having the countryside digital elevation model, and there is a canopy model from the single photon LIDAR at 2 and 1 m spatial resolution respectively. So, that enables the area, shows the 3D topographic detail along with the A. So, river valleys and the ridges you can see easily, but here you can see in the forest structures the grey patches represent the non-forested land cover classes that we are detecting through this LIDAR. So, LIDAR can give the actual and the deeper area of the target. So, another is the chip scale atomic clock, that is the oil and the gas exploration in the harsh environment and may also benefit from the highly accurate atomic clocks which measure the time using the frequencies of the well defined atomic transitions in the element such as Celsius or the rubidium, cesium and the rubidium. So, you can see here this is the various chip scale atomic clock. So, in this chip scale atomic clock, what we are having? We are having the various sensors are attached with each other, and that will just give the brief idea. So, atomic clock can be made sufficiently small for integration into the devices. So, we are having a various atomic clocks. So, volumes as low as 16 centimeter cube with the power consumption less than 120 milliwatt. You can imagine how small or thinner atomic clocks we are using as a sensor, that is dubbed chip scale atomic clock. These atomic clocks is dubbed into the chip scale atomic clocks and are used in the range of application from the oil exploration to the national defense. So, these atomic clocks are used for the various in the various areas. So, for example, there is a company who has developed the CEC-UGC for underwater oil exploration using the techniques known as the ocean bottom seismometry, that will be OBS, and here the underwater mapping is achieved by placing the sensor into the ocean floor. Moreover, we can use for the sound waves also. So, sound waves that will be sent from an above water ship at the various angles and seismic activities resulting from these waves is detected by the sensor. So, that activity, seismic activity, will just give the brief about the depth of the seas. So, by using these sensors, we are having the highly accurate time keeping a 3D map of the underwater area that may be obtained from the sensor recovered from the ocean floor. So, by these sensors, a ocean floor mapping can be easily done. And that will be used for the further processing. As a consequence, CEC has emerged as a existing commercial quantum sensor for the oil and gas exploration. If we were able to see the mapping of the ocean floor, then it is easy to detect the oil reservoir there as well as the gas reservoir there. So, it is easy just to detect the various oil and gas exploration by using the quantum sensor. Another is the photosynthetically active radiation sensor, that is as also known as the PAR sensors, and that are relatively mature quantum technology that measure the photon flux density in the visible light range, that is suitable for the photosynthesis. As we are talking about the photosynthesis, so we are using the daylight. So visible light, that is in the range of the 400 to 700 nanometer, and that is typically using a silicon photodiode detector. Now you can see this is the shape of the silicon photodiode detector, and you are seeing that there is a light ray which is falling upon the photodiode. So what are the application of this PAR? It is used for the agriculture monitoring, it is used for the photovoltaic systems, it is used for the environmental and ecological research. So by measuring the light intensity for optimizing the crop growth and accessing plant health. So that sensor is used, PAR sensor is used for the agriculture monitoring. Also the monitoring the solar radiation for efficient solar energy generation, this photo used in the photovoltaic system. Another, collecting the data on the radiation level to support the environmental studies and ecological conservation efforts that can be done through the environmental and ecological research. So these are the various applications. So several companies including the Leak or Sky Instruments, and they are the various companies who are just working and manufacturing commercially PAR sensors. So PAR sensors have been used in the multiple bio-based CO2 and mitigation studies, which is a topic of the significant interest of the fossil energy as well as the industry, as the companies try to monitor and mitigate the greenhouse gas release. So PAR sensor measures the photosynthetic lights levels in both the air and the water. So we can measure the photosynthesis light in the air as well as the water. So the sensor responds to visible light in the spectral range that is used by the plants in the photosynthesis, that may be 400 to 700 or 375 to 630 nanometer. So it features a waterproof sensor and the head and concentrator that will be used for report the photosynthetic photon flux density, which is measured in the mu mole, meter inverse 2 and second inverse 2, means micromoles of photons per meter squared per second. So this the sensor is calibrated for use in the sunlight only, but can also be used to measure the PPFD from the electric light sources, and this sensor is ideal experiment that investigate photosynthesis and primary productivity and can also be used in many agriculture and environmental science applications. Thank you very much.